Telkom University as the #1 private university in Indonesia under the auspices of the Telkom Education Foundations, a subsidiary of PT Telekomunikasi Indonesia. Established on 50 hectares area in the southern of Bandung, Telkom University is a merger of 4 institutions under the Telkom Education Foundation in 2013, namely Telkom Institute of Technology, Telkom Institute of Management, Telkom College of Art and Design Indonesia, and Telkom Polytechnics. Having a number of students reaching 30,000 who come from all over Indonesia, Telkom University has sufficient to be a research and entrepreneurial university in 2023, which actively involves the development of technology, science and art with information technology based. Its missions are to organize and develop international standardized educations with technology-based informations, to develop, disseminate, and apply internationally recognized technology, science, and art, to utilize technology, science, and art for the welfare and advancement of the nation's civilizations through the development of entrepreneurial competences. Until today, Telkom University has had 50,000 alumni spread all over the world. The number of alumni has been calculated since 1990, which was the beginning of the STT Telkom campus, with 7 schools in it, namely School of Electrical Engineering, School of Industrial Engineering, School of Computing, School of Economics and Business, School of Communications and Business, School of Creative Industry, and School of Applied Science. Telkom University has 34 study programs ranging from diploma to master programs, of which 59% have been internationally accredited. Furthermore, Telkom University is also the first campus in West Java that is accredited A from the National Accreditation Board of Higher Education. Ranked 9th in the Green Metric UI ranking, as a green campus in Indonesia, Telkom University has earned various achievements, including the #1 private university by the Ministry of Technology, Research and Higher Education in 2019. Telkom University also acquired Anugerah Widya Padi as the campus with the best innovation for the last 3 years since 2017, and ranked #1 private university at the level of 4 ICU Uniranked and Webometric. In addition, Telkom University also received the title of 5 stars by the QS Star for the category of technology, inclusiveness, employability, and innovation. In terms of publications, Telkom University also acquired the highest international ranking of publications from Simago. It also won a Sinta Award from the government as a private university with the #1 most productive publications in Indonesia. In line with the vision to become a research and entrepreneurial university in 2023, Telkom University continues to develop in the field of research and innovations. With the establishment of Bandung Technopark, Telkom University continues to strive in creating startups and innovations in order to continue and to contribute in supporting the industrial sector in Indonesia. In addition, Telkom University is also supported by the establishment of the Research Center in order to produce the best innovations. The existing research centers are Research Center for Advanced Wireless Technologies, Research Center for Internet of Things, Research Center for Digital Business Ecosystem, Research Center for Human-Centric Engineering, and Research Center for Advanced Creative Networks. Furthermore, each faculty at Telkom University also has its own research group. Each of them is In supporting the entrepreneurial ecosystem model in it, Telkom University through Bandung Technopark has given birth to approximately 42 startups generated through the ecosystem model in it, through the following process. At present, Telkom University also has an international program, in addition to international classes with 9 study programs. Telkom University also has a global academic program which includes student exchange, staff exchange, and joint or double degree. Besides that, from community service and research, Telkom University also has a global research and community service program with several countries in Asia and Europe. Until now, Telkom University has collaborated with 57 international partners from 3 continents and 10 countries. Telkom University has digitalized the learning content through the Center for E-Learning and Open Education. It has 637 learning subjects produced from its 9 studios.
Hi, I just wanted to check if my sound is working and if you can hear me. Okay. Um, okay, Saeed, so whenever you are ready, we can start. Depends on how you want to run things. Um, um, okay, so I'm gonna assume, since I haven't heard anything on the other side, that we should just get started and dive in. And hopefully, if there's any problems, then just please let me know. Um, I have this door behind me open just to let some air into this room. If it starts getting noisy, please ping me again on the chat, and then I'll have a look, and then I'll just close the door. And again, just like yesterday, I am looking at the chat so we can, any questions you have, you can put them there. Again, I'd love to hear your voices and to have you speak. And so I'm going to also open the participant list on the side. And yeah, let's just take it um, there. So yesterday, okay, good. No noise, so that's good. So yesterday we began with these first two parts on Bayesian learning, on basics and computation. And today for this next 1.5 hours, I thought we could do a little bit of tricks where we can learn to manipulate some probabilities together. And then these kind of tools are maybe one of the kind of tools that you should develop over the course of your career in machine learning. They're tools that I'm introducing in the concept or in the framework of Bayesian thinking, but they appear in many other kinds of questions and many other places and problems. So they have a generality. So if you can learn to become flexible with these kind of tricks and tools, then I think that is sort of one way of having a fun kind of contributions to machine learning that always keeps you learning, finding new things, exploring, and making your contributions to our field. So today we're going to look at some of these Bayesian tricks, although as I said, they're more general. So the outcomes are three things that I want you to take out today is to think about the question of representing distributions. And this is the question that I have for you all again this afternoon as you're all coming back and getting ready. So just think of your answer to what a distribution is. I wanted just to review again some of the integral problems that I briefly showed yesterday, just so that we see how it is that those problems fit and arise, and some of the problems that we'll try and deal with. And then we're going to look at maybe 5 or 6 different kinds of tools for manipulating probabilities, and we're going to do some derivation together. So if you have a pen and paper close by, bring it now already, and then we'll do these derivations together as well. Um, so let's dive in. Yesterday, I said the problem of inference is the one of connecting the data that you have measured or observed to the model that you have built. And then those kind of inferential questions then are either direct or indirect, and then they ask you questions about computing probabilities of the data. So the problem that we studied a lot of, starting with De Finetti's theorem, then moving on to questions of the marginal likelihood, and how it is that we actually do posterior computation was to compute the evidence, P of x, which integrates over any latent variables or any parameters of the model. So this one is the basic computation, and so much of Bayesian thinking is centered around this question. We obviously may also want to do moment computations, and actually a lot of things that we're going to do today are about these moment computations or computing averages. So again, when we read this integral, it was computing the average of the function z under the distribution pz given x. And so there's some conditioning here. You may not have conditioning, it depends. So computing averages like this is important. I will close the door. So computing these averages is very important because they let you compute the mean and the variance, but they also will be very central to many other problems. For example, you'll see this problem in variational inference, you will see this problem in reinforcement learning, you'll see this problem of computing moments and means and expectations in various other ways. Parameter estimation, as I said, was the core question of Bayesian methods, where we wanted to compute the posterior distribution of some parameters given the data. Prediction, here I wrote it in the temporal model, a time series. Given the sequence of time 0 to t, can you predict xt plus 1? And behind this lives maybe different kinds of models, autoregressive models, latent variable models, recurrent neural networks, many other things. And there's the integration of all those other things has already happened to do this prediction. Planning, maybe later in your course of lectures, you will see some problems on reinforcement learning or control, and you will always see this kind of problems where you have a cost function or a reward represented as C, and then integrated over some initial state and some actions, and you want to integrate or average over time. And so this is important, and then you average this under some policy, which is choosing U and X. And then I mentioned hypothesis testing yesterday. So you want to compare different kinds of hypotheses using the Bayes factor, and you will compute this log difference. Or you have other questions like in experimental design in the applications that I mentioned, that you are, before to decide where you will place a sensor or where you will take do the next experiment or take the next measurement, you want to make an assessment if doing that experiment will actually give you the maximum amount of information. And so this kind of information gain then becomes a very important quantity here. So again, as I said, inside these questions lives a series of integrals. The integral here of computing the marginalization, the integral here of computing the expectation, in computing the parameter estimation to normalize this distribution involved the computation of an integral already. And so everywhere in the KL divergence here, there is an integral. So there are many integrals hidden everywhere. So one of those questions that we're going to ask is how we can represent these distributions that are involved here, these P of Z given X's, and then also how it is we can compute these integrals and do these averages under these distributions. So yesterday, a few of you mentioned decision-making in your definitions of machine learning. And I wanted us to think just a little bit about what the difference between inference and decision-making is. On one hand, and most of what I've spoken about and will continue to do so today, is this question of inference. And inference in some sense is about what you can know about your data. Given a set of data, can you know the parameters of a model that have generated? Can you know the future states in some sense? Can you explain them? Can you know the distribution of latent variables? Inference alone, though, is not enough. And that's why I wanted us to introduce the concept of decision-making. In decision-making, it is about what we can do with our data. And doing is a very different kind of thing. It relates to action. It is this question of information gain and reinforcement learning and control that I just mentioned. But to do the decision-making, you do need to have a process of inference. So they are very tightly coupled. And I say that once you have these two ingredients, and Bayesian methods in particular give us the way to do both tools of inference and decision-making, we can build systems of plausible reasoning. I'm using this phrase plausible reasoning from the opening chapters of a book called Bayesian Theory by E.T. James. And if there's one book that you want to read, just go and read the first 2 chapters of this book. I have the reference in the end. And to do these kind of plausible reasoning, we need to have flexible ways of building probabilistic models because they give us ways of interrogating evidence into our models and decision making. And so this raw probabilistic modeling and accumulating evidence becomes important. We have ways of making consistent inferences, that they are reweighted in the correct way, that we can correct for biases and systematic undersampling using the likelihood function. We are insensitive to parameterization, as we looked at yesterday. And we can maintain these beliefs, which means we are maintaining probability distributions over all quantities that we think are interesting, and using those in this Bayesian kind of way to then compute expectations and predictions, and that we can reason about potential outcomes and take actions, this question of decision making that I just brought today. So I wanted just to focus again on the question of inference, but I wanted to just put this point of decision making really in front of your mind, and you will study this kind of decision making in many other areas of utility theory, in economics, in reinforcement learning, in control, to add, and causality, to add a little bit more. So yesterday I said when you had to think about this framework of Bayesian thinking, which asked you to think about the kind of models that you are building. There are various kinds of models, from directed and undirected to latent variable models, generative models, and discriminative models. I mentioned the second part was about learning principles and the role of statistical inference. And then for any given model, you can combine it with many different statistical inference methods. And I said that statistical inference for me has 2 different forms. There are direct inferential methods and indirect inferential methods. So the direct inferential methods are methods like the Laplace approximation that we looked at yesterday, which said even though I may have complicated distributions and complicated functions, what I will do is fit the closest fitting Gaussian approximation to that distribution and then compute integrals under that Gaussian approximation. And we also looked yesterday at maximum likelihood, which is taking the log of the likelihood function, and maximum a posteriori, which said that actually to address questions of overfitting in maximum likelihood, we would introduce questions of regularization and prior distributions. And today we'll do a little bit more, and then there are many other methods. You can extend the Laplace to integrated nested Laplace approximations. There is the EM algorithm, which you'll see in other places, and then Markov chain Monte Carlo, which is one of the workhorses of this particular area, and important for Bayesian thinking, that if you wanted to be fully Bayesian, that is, know the distribution of all things in your model, you would combine this. And yes, I'm just continuing the slides from yesterday here in this set. Indirect inferences then don't try to directly compute P of X. What they try to do is to look at P of X in relation to how it changes and behaves with respect to another distribution that you know. So looking at how things work relatively can sometimes be an easier thing than looking at things completely and absolutely. So it is sometimes much easier to compute P of X divided by a different distribution Q of X than it is to compute P of X directly. So that's what indirect methods look at. I won't mention any of them, but these are some of them. Two-sample testing, which comes from hypothesis testing, and another method which we call approximate Bayesian computation, which is particularly useful. And indirect methods themselves are useful when you have models that are simulators of a system. So they aren't a likelihood-based model. They are made likelihood-free models or a simulator like those differential equation systems for COVID physical distancing that we looked at yesterday. So don't worry, most of the things that you will see probably throughout the week are direct methods, but do keep in mind that there is this sort of this growing area of indirect methods coming up. So I want you just to take a minute again, and the question that I have for you is, how do you represent a distribution? How do you represent a distribution? So please take 1 minute just to think about this question, and then already start writing your answers in the Zoom chat. And for any of you who would love to, again, hear your voices and hear how you explain your answer to this question. So already please raise your hand and then a few of you can speak, and it would be great to hear from you. So how do you represent a distribution? Mhm. Okay, so some time has gone by. Let's read a few things and ask a few of you to speak. Robbie says plotting the data, so that's really good. Plotting the data is a really important way just to understand what's going on. As a function with respect to time and other parameters specific to the distribution. So Vishal, maybe you can raise your hand and then just explain to us a little bit more about what you were thinking in your answer to this question. Vishal Gupta, if you are able to speak, then just raise your hand and maybe Saeed will help you unmute yourself. Then I see there is Iqbal who says a histogram or a scatter plot or a QQ plot. So that's really good. Tisa City says spreading the data into the method. Paula says with a histogram. Saeed says using some known distribution with parameters derived from observation. And Saeed, maybe you can also unmute yourself and tell us a little bit about what you were thinking here as well. And let's see, a few other people are saying find the pattern in the data, getting and plotting, arranging the data from min to max, using a parameterization, and Vishal is asking how to raise his hand. So that's good. That's great to have you here. That means hopefully this will work soon. So Vishal, can you go ahead?
Hi. So according to me, distribution is represented as a function with respect to the time or whichever parameters along the x-axis, and often distribution is, if you would consider 2D distribution, distribution is where the value of the distribution at a certain time, at a certain value of t, is represented in the y-axis. And there's a function. The function itself consists of t is a function of t and other parameters. So if you were to consider the Gaussian normal distribution, there you have mu and sigma. Or if you were to consider the gamma distribution, of parameters there, or the beta distribution, and hence, yeah, or the Poisson, where you have lambda.
Thank you very much. I think this is really good. I think you bring some interesting points in your explanation that some kinds of distributions are parameterized. They have a set of parameters, and then we can plot those parameters and look at how they're changing if we know what that parameterization is. Saeed, I think you also had a question, which is maybe, or response. Maybe you could tell us what you were thinking.
I think it's a bit similar with the previous one, that, for example, you said like yesterday, you represent the coin with the Bernoulli distribution, and then you can derive, for example, the parameters from the observation.
Right, so I think this one is also good that you can, some distributions, Vishal was telling us about parameterizations of distribution, that means invariance, but sometimes you don't know those things, but by simply observing things, you can get a sense of the distribution. So distributions can also be represented by sets of observations. Maybe if Novi Novri, Suhermi, if you could also speak and tell us a little bit about your response, where you just wrote the data generation processing, would be great to hear from you. And Ariane says nth statistical moments. Can we also plot the KL divergence from Abuka? I don't know if Novri, if you can speak.
Yes. Okay. Yeah, I mean, that data generating processing, we basically, well, we have a distribution, and in order to represent that distribution, we could sample data from that distribution. So that is what I mean about data generating process.
Thank you. That's great. So yeah, if you know that your model is somehow representing a distribution, and it may be because there's some kind of variation in the data, there's just some noise and variation, you can just sample. So many of you are picking up on this idea of using samples as one way of representing. So thank you, everyone. That has been a great set of responses. Let's go through that systematically, and I think the set of answers that I have here will cover everything that you have all thought about and maybe a little bit more. So this is sort of the idea that Vishal put forward, and actually several others of you as well, when you were thinking of parameterizations and parameters of distribution. So this is the beta distribution, exactly the example that was mentioned, that we do have some distributions that we can represent in analytical or closed forms. Distributions need to have special kinds of properties. We said they must integrate to one, so they must be proper in that sense. And we need to be able to know their normalizing constant. So we need to be able to know their closed form normalizing constant. So this means that there aren't that many distributions that we do know in these analytical or closed form versions. Typically, they're all models which are going to be linear models. So A transpose X is going to be a model that we can create an analytical distribution of, or quadratic functions. These are typically two things in mathematics we know how to integrate. And so you will see that if you look at it in the form of the exponential family that we looked at yesterday, which is one very powerful class of closed form and analytical distribution. They have this property that they are exponentials of linear functions of sufficient statistics times some summary statistics, some natural parameters, and then you can integrate in those forms. So many of the distributions you study will be of this class, and the ones we looked at yesterday as well. Yesterday, we also looked that you can represent distributions by approximating them with an analytical form. So the Laplace approximation was the one that we looked at yesterday, where you have this kind of distribution that is a bit skewed. And instead, what you would do is you find the map estimate, you compute the curvature of this model using the Hessian that we showed using the Taylor approximation yesterday, and you fit the closest fitting Gaussian. And this now, you then get a Gaussian distribution, which is in some sense a match to the real distribution that you actually had. It's not perfect. It obviously has some bias. It has error in it. And so whether or not that's a good representation or approximation of your distribution is a question that depends on the kind of application you're working with. The one that many of you mentioned is to do histograms, is to do plotting, is to look at the sample frequency of your data. And then going back to some of the concerns you all had yesterday, this is a very frequentist way of looking at distributions and data, in a very powerful way at that we can just look at distributions by sampling collections. So we may not know the function, but we know where actual samples do as the generating process came up. And then we can represent them in these kind of ways, either by histograms. Here's a contour plot from a KDE sampling as well. And then the final one, which maybe is where a lot of machine learning is going to, is that you can represent a distribution. And again, many of you mentioned this, through a sampling procedure, that instead of representing in closed form or as an approximation or as a set or collection of samples, you represent it as a program. So this is a very famous way of representing a Gaussian distribution by squashing a uniform through a CDF function, and then you get a Gaussian distribution. So this is the simplest one. And you get many other ways. The modern machine learning generative models, normalizing flows, GANs, operate under this idea of learning a procedure to do sampling, and that can represent the distribution for you. So let's just look at some of the questions that Untari Novia is asking. If the data has very large dimensions, what is an effective way to find out the data distribution? And I think this is a really, really important question. In very high dimensions, computing the histogram like this is sort of very hard to do, because what you will then need is to scale the number of samples that you have. You know, it's usually some kind of square root function with respect to the number of dimensions. So as the dimensions are increasing, the number of samples that you need is also increasing at a very large rate. So high dimensional problems in statistics are in general a very big problem. So in that sense, you may want to have more closer to analytical forms or approximation forms, or even these sampling procedures. They are both ways of handling high dimensions in more flexible ways, because if you have an analytical form, you can control the dimension in certain ways, and then all dimensions are actually given the kind of weight. Again, as I said, it depends on the problem that you have, whether or not those dimensions, those approximations are good or you are handling them. But that's not to say that you can't use sampling-based methods in high dimensions. And there are other ways of controlling where it is you're sampling, using this idea of information gain, that if I have samples of this mode that I'm looking at here, maybe the next sample that I take should not be here, should be somewhere else. And you can use certain kinds of search methods to solve those kind of problems. And in fact, Markov chain Monte Carlo is one of those methods. It is a search method to help you be more clever about where it is that you generate samples, particularly in high dimensional distributions, but high dimensions are in general a problem. And then as Georgios is mentioning, maybe part of the problem is to reduce the dimensionality. Again, this will depend on the distribution and the kind of model that you have. Many data that we observe that are very high dimensional do live on some lower dimensional underlying manifolds of data, and then it's better for us to learn and compress the data using methods like PCA and others to solve those problems. So I think dealing with high dimensions and high dimensional problems is one way, and actually the problem of computing integrals addresses directly this question, or is concerned with this question of high dimensions. And so that's why we're going to spend a lot of time on approximations and how it is we learn tricks of manipulating integrals. So I want to just take a minute to look at Monte Carlo methods a bit more in detail, because it is going to be the basis of almost everything you do in machine learning. Monte Carlo is everywhere because of how it is that it allows us to compute integrals. So the Monte Carlo method is one of the most general methods for computing summations, integrals, and probabilities. So here we have an integral problem, which is a function f of theta. So it is a function of some parameters theta, and it integrates the function f under some distribution p of x, and I'm integrating dx. So I'm going to write this in this integral, in this expectation notation. Again, it's the expectation of f under the distribution p, or averaging f under this distribution p. Now, if you don't know how to integrate p and f as you normally have, let's just put actual distributions. Let's say p of x is a Gaussian distribution, and f of x is, I don't know, some fourth order polynomial. You know, if it was quadratic, you'd be able to solve that. If it was exponential, if it was a cosine, you'd be able to solve the integral. But let's say it's even f is a deep network. It's a set of convolutions put through a set of series of nonlinear functions, ReLU functions, sigmoids, tan h. So then you won't know how to do that kind of integral at all. So then the Monte Carlo method says it's very simple. If you want to compute this integral, you want to compute this average, draw samples from P, So you need to know how to draw samples from P, and then compute the average of F at those sample points P. So if I write this in equations, here's the distribution P, generate a set of capital N samples, what sometimes we'll call them variates, xn from this distribution. And then you just compute F at each of those points, take the sum, divide by n, which is about computing the average. I'm just going to go back and spend a bit of time. So I just wanted to stare at this very carefully. This same integral is in the integral that we all use when you compute a mini batch. The distribution here is the whole data set, so you can sample from the data set, and F may be the model that you're actually interested in. So when you do SGD, what you do is you sample n data points from the full data set. That gives you the set of n, and then you compute either the function, you forward pass through the function, and you compute its gradient through this kind of average. So this method of computing integrals is everywhere, from the basic methods to more complicated ways of doing Bayesian analysis. And as I just said, there are some key requirements that it's asking of us. The reason we do Monte Carlo is because it should have 4 kind of properties that we're interested in. One of them is called consistency, that even though this thing here is just a sum, so in the end, this f hat is actually itself a random variable. And the reason it's a random variable is because you can generate many different types of, many different sets of size n by sampling different times from this distribution in different ways. So this is a random variable because it depends on the specific set that you use, and you can use many different sets, and you can average over different sets of n as well. So what you just want is that this estimate, the sum, should converge to the true value of the integral. We usually don't worry about this because the law of large numbers means that when you take n to infinity, this will typically be true. It will converge to the true value. The one that we're actually very interested in is this question of unbiasedness, that if I generate any set n samples x hat n, and I compute this value, and we do this many different times, and then compute the average of all these f hats, the average or the mean will be centered on the true value, so that you should get the correct value on average for these kind of questions. Again, because this is a random variable, and that means that random variable has itself a variance, we would like and prefer to have these kind of estimators that have low variance. Because they make it easier to compute, they give us more trust in the method, it reduces noise downstream in other kinds of learning that we are doing. And then finally, we want to have ways that are easy to compute using this method. So we need to have distributions that are easy to sample from. If we don't know how to get samples x from the distribution we care about, whether that's the data, so we sample it just by measurement, by sampling from distribution, or it's a Gaussian and we don't know how to sample. If it's something more complicated, then that makes computing this estimate very difficult. And so part of the research of Markov chain Monte Carlo methods is then to figure out, well, how do you generate just from distributions that are very complicated that you won't know how to sample from. And then you also want methods, you also want it to be easy to evaluate f. If f is a deterministic or analytical function, so it's a program that you can evaluate, then this will be easy to do, it's parallelizable. But let's say f is not a program. Let's say f is an actual experiment in the real world, or it is a robot system, and you have to evaluate these samples in the robot system, then this might be very expensive to do. You can't do this very easily. So then we may have to think of other methods of computing these integrals, or again, if we have low variance estimators, then we can use a very small number of samples n, and that means we can use very few evaluations of the function f. I want to just very briefly mention, and let me just make one last point if I can, of why this is important. In many and almost everything we do in machine learning, ultimately we're going to try and change the problem so it is of a form of a product of something we want to evaluate times something that we can easily sample from. And you're going to see this in the tricks that come later on, that we always are going to try and change the problem to be that form, because if we can do that, then we can do the Monte Carlo method, and then we can compute these integrals using this Monte Carlo estimator. And that means we can actually compute the values of the integrals, and we can do learning and compute gradients. So I think that's very important just to keep in mind that we want to always keep things back or transform them into ways that allow us to do the Monte Carlo method. A very different way are variational methods that I just wanted to very briefly mention. That you may have a complicated distribution here. And of course, if we knew this distribution, we wouldn't have a problem, it would be solved. So we can't know these distributions. So variational methods are a very general class of methods. They say, I'm going to create a class of distributions, and I'm going to search for the closest distribution in that class to the true posterior distribution. And I'm going to define some measure of distance or goodness or closeness. And typically one definition is to use the KL divergence, although there are many competing definitions that we could use for that. And so variational methods are very popular. Instead of the Monte Carlo method that we saw before, they were going to give us deterministic approximations rather than stochastic approximations. And they're typically going to deal with bounds on probabilities of interest. And so again, there will be some errors, and we need to think about those kind of errors. And then we'll introduce some deterministic parameters, these phi's, and we call those variational parameters. And Monte Carlo methods and variational methods also get combined in many different ways. And I'll show you some of that a little bit later on. So you may just want to just keep a bird's eye view of some of the ways that we have to compute these kind of integrals. One set of methods are called large sample approximation. So you just use the asymptotic properties, you send n to infinity, and then you look at how the integral changes when n is large. And so you have methods like Bayesian information criterion, AIC, maybe you've come across these in other cases that fit into these kind of large sample approximations. Then you have another kind of axis, which are stochastic methods. These are Monte Carlo or Markov chain Monte Carlo methods that we have seen, and Laplace approximations, well, integrated nested Laplace, that sit there that use sampling and use randomization as a way of computing these integrals that we looked at. And then the third class, which are deterministic, like the variational methods, which try and fit an approximation to those integrals that you have and give some flexibility to do those. And in that space, there's a lot of different kinds of things that are possible. There are the methods, Laplace's method, Chip's method, hybrid Monte Carlo, annealed or plain importance sampling, expectation propagation. So many, many different kinds of inferential methods and methods to compute integrals that you all have to explore as you become more familiar with machine learning and as you keep learning and exploring different areas of research. So we're going to now switch our tack, and we're going to do a bit of a dive into a set of different kinds of tricks to manipulate probabilities, probabilistic quantities, and kind of things that you're going to see coming up once in a while, or actually more regularly, depending on which framework of work that you're going to do. So if you have some pen and paper ready, then please grab them right now and write out all the equations that you're going to see for the rest of the lecture with me. It will sort of help you get used to writing the notation, find the mistakes that I have made and probably will have made in these kind of slides, and then also it will help you ask certain kinds of questions, and we can clarify them together as we go along. So here's one, it's one I like. It is from an area that we will call randomized linear algebra, or just randomized methods in general, and it's called Hutchinson's trick. And so Hutchinson's trick is about computing the trace of a matrix. How can you compute the trace of a matrix? Very easily. And now, obviously, the trace of a matrix is just to take the sum of the diagonal elements of the matrix. So now that's pretty simple to do, except that if you don't know the matrix already, for example, what you'll often see in anything you do with a Gaussian is to compute the gradient of the log determinant of a matrix X. And maybe sometimes in a Gaussian, how that will be, it's going to be X inverse times some other matrix, or a vector, or something of that form. So this thing inside the trace is a matrix A, but you don't know it directly. and you'd prefer not to first compute the inverse, then compute the other gradient, then do the multiplication. What you'd like to do is find another way that helps you directly compute this without doing the expensive computations of computing the inverse and then computing the matrix and then doing the multiplication. So this is the thing we want to do, is try to figure out a trick to do that kind of manipulation. So again, the gradient of the log determinant of x is equal to the trace of x inverse times the gradient of x. How do we compute this kind of trace? So here's the trick. I'm going to simplify so that we understand how the trick works and how we understand randomization. The trace problem is to compute the trace of a matrix A. It can be of any dimension that we like. So it's not particularly cares about the dimension, but later on the dimension is going to matter when we want to do an analysis of this. So one of the properties of unit mean, zero mean, unit variance, random variables, is that if you take a distribution, any distribution, and you sample it, let's say it's a Gaussian, and you compute z transpose, and you compute its average, that is going to be in expectation the identity matrix, right? And this is because they have zero mean, so it is going to be 1 on the diagonal and 0 everywhere else. So this then becomes a very important quantity for you to look at. So if you didn't have a zero mean, there would be another quantity which would be MM transpose, because M is 0, that's why it's zero mean, and because everything is a unit, it's just 1, it's not going to be a generic sigma, you just get ones on the diagonal. So this is the kind of thing we're going to do. It's a very powerful trick you find in almost everywhere in machine learning. How can you multiply something by 1 and then change things around? So this is what you call the identity trick, and we're going to use it 3 or 4 other times for the rest of the lecture. I'm just going to multiply this trace of A times the identity. Of course, I multiply by 1, nothing changes. But I know that the identity is equal to this expectation. So I actually can multiply A by the expectation of Z transpose. And again, Z is a sample from some unit, zero mean, unit variance distribution. And I can easily do this for all of them. Now, the property of the trace, and actually the property of expectations is that the property of expectation, that is a linear operator. So I can actually take it out of the trace and the expectation, which is what I'm getting here. Expectation of trace of A, Z, Z transpose. So again, nothing has changed. I still have my initial problem. And now I'm going to use the trace property, which says that I can actually do rotations. Traces are invariant under circular rotation of the multiplication. So I can take the Z transpose and put it on the other side. So I'm going to get Z transpose A times Z. I think there's still a trace that should be here. And so then this is the property of the trace that I can compute it in this way. And so this now is the trick for computing the trace. Sample a Z randomly and compute Z using systems of linear equations. So I just need to do now multiply A times Z, which is a very simple linear operation, and then multiply Z transpose by A. So one of the distributions you can sample from is called a Rademacher distribution. It is just a set of samplings of 1 and 0s that you can get, but you have other methods as well. You can sample from a Gaussian, and the choice between the Gaussian and the Z will be how many of these Zs you need to compute, right? The final step here is to do the Monte Carlo trick, to sample Zs, many Zs, compute this value for all of them and do the average. So you can see that if you were to compute this X inverse grad X, you'd now multiply by Z transpose and Z on both sides, and you would just solve systems of linear equations instead of doing complex eigenvalue or cubic numerical methods. And so this then is sort of one of the first kinds of tricks that you can use. And it's there. I'm bringing it to you to introduce you to this really amazing area of randomized linear algebra, to see the power of multiplying by 1, which sort of expands our range of things and manipulations we can do. And then how the Monte Carlo method reappears in ways to compute something that you think was just a very simple linear operation through averaging, you can also compute this kind of trace. So, write a piece of code and actually test this thing for something that you do in a notebook, and check for yourself to see how many samples you need to get a good average estimate of this trace, and that will give you a good little exercise also in manipulating probabilities and writing cleaner and better code. So if you're ever working with Gaussian processes, you'll find this problem comes up all the time. And this is a trick then that you can often use in those methods. So I just mentioned this identity trick, which we just use in Hutchinson's method to multiply by 1. And I want to use this trick again and now use it in sets of integrals directly. So the integral problem that we have been looking at very often is compute the integral of some function f multiplied by a distribution p. Again, that was the expectation of f under the distribution p. Now, we may not know how to sample p. P may be a very complicated distribution. It may be an unnormalized distribution. It may be various kinds of, it may be a simulator of a model, or we may just only have measured the data so we don't know the distribution. So we may want to instead change this integral to be an average under a different distribution Q that we actually know how to sample. And doing this averaging of a different method, how we actually switch from an average under distribution P to an average under distribution Q is again to use this identity trick to multiply by 1, so to divide by P, which is what we're going to do here. And that trick is then going to let us manipulate the distribution in different ways. So let's actually do this to compute an integral. So here is a very popular question, one of the same question we have been asking all the time, and it will come up in many methods like latent variable models, as well as just computing the average of any function. So here's the integral problem. Again, if you are writing out the equations with me, then we can do them slowly together. The sum function m is an integral of a function f of z times p of z, and I'm going to integrate over the random variable z. Now, as I said, what we want to do is to not do this integration under a distribution p, but to do the integration under a distribution q instead. So what I'm going to do is multiply and divide by q. So the integral is exactly the same, but this is going to let me do a set of manipulations. So if I just regroup this integral, I'm just going to now have the integral of the function f of z, now the ratio of p of z divided by q of z multiplied by q of z. So again, I'm just rewriting how the integral is appearing. Again, this is a new ratio instead. And this ratio is going to be very important. Kind of ratios like this you're going to see everywhere in machine learning, and we need efficient ways of computing them. So there are some conditions. Of course, if I'm going to divide by anything, I need to make sure that that thing is 0 or greater than 0, because I don't want this thing to become infinity when I divide. And I also want to make sure that this quantity at the top now, f of z, p of z, whenever f of z, p of z is not 0, q of z is not 0, just so that the rates at which they are growing match each other. And this integral is actually a proper integral, that it can actually compute it and has a value. And in this case, what you want to do is to make sure that you choose a q that is something that you can sample from, that you know how to evaluate. So then this, just writing it in our expectation notation, now becomes an expectation under a new distribution q, which I know how to sample from easily, multiplied by this new modified function, which is f of z times the ratio p of z divided by q of z. Now, let's just do that. This is the basis of what is called importance sampling. And if you just now apply the Monte Carlo method to this expectation or this integral, what you're going to do is sample from the distribution q to get some sample zs. So you're going to generate capital S or capital N of these samples. You're going to compute this importance weight, which is this set of p divided by q. And then you can just compute the weighted average. or the weighted sum, which is 1 over s times the sum of the weighting function times f of s. And in the log, which we're often going to be interested in, I'm just writing it so that you just see how that quantity comes up. So this then is pretty important. There's some properties of important sampling that we spoke about, and you'll see this identity trick appearing in many places and actually using this idea of important sampling when we're going to manipulate stochastic gradients, when we're going to derive probability bounds, if we're going to do some theory. In reinforcement learning, there are ways of computing corrections of probabilities that will come up, and so we use the same idea there as well. I'm going to do one last trick and then we're going to take a bit of a break. So these are called probability flow tricks. So the question that I'm going to ask is that if you start with some distribution Z that you know, let's say it's a Gaussian distribution, and I push that distribution through a set of known transformations, Z, K of them, let's say, what is the distribution at the end of those K deterministic transformations? So here's the distribution. I want to have a sample from this distribution. I'm calling it X here. I'm going to transform it through some function G, and I get this distribution Y hat. What is the distribution of Y hat? So there is a thing that we call the unconscious statistician, is that if you wanted to compute averages under this distribution P, under this transformed distribution, you don't need to know the distribution Y. What you can do is just compute averages under the distribution P and just pass it through the function f of x. So you could just be unconscious. You could just, well, use the original distribution, sample it, just pass it through your function G, and then just carry on. So how you will do that is to exploit the rules for change of variables. This becomes very important. It says that if you have a distribution X, like P of X, and you want to go to know the distribution P of Y, the P of Y is going to take P of X and reweight it by this inverse of the determinant here. So I'm going to compute the derivative dg dx and compute its inverse. So this is just the standard rule for change of variables that comes up in calculus and also in probability. So the kind of things that we will do here is to begin with a diagonal Gaussian, and we improve it through this change of variables. So that's what this picture is showing. I start with the diagonal Gaussian. I choose a G function that is kind of complicated, that's mixing dimensions, and then I can get a far more complicated distribution. And that's another way of representing a complicated distribution. And the reason this is interesting and easy to use this change of variables is that it's going to make the entropy computations easier, because I can compute the logs and just do the average under this P. And one of the things that you're going to try and do, that these Jacobians, you want to define these functions G so that they are triangular in some sense. And the reason they should be triangular is that it's easy to compute determinants of triangular functions. So here's just an example of what is called a planar flow for this function G. In deep learning, you'll recognize this as a residual network. It says that to make a function a transformation function, what I'm calling Z here or G here, I can just start with the identity and then make some linear transformation of W transpose Z, where I'm introducing some new parameters W, B, U, and some squashing function H. And so you can do this kind of exercise, compute the log determinant of this function f of z here. And so the property of the determinant, and you can do this as an exercise later, is to say that the determinant of the identity plus AB transpose is this question. So you're going to use that property to do that. So, and then later you can just compute this for yourself to just show that if you can compute determinant of I plus US transpose, you can get linear time computations of the determinant and their gradients. And linear time, which means order of n variables, not n squared or n cubed. And that's the kind of thing we need to make these advanced computations. So I know that may have been a little bit difficult just to follow. But again, they are just exploiting this rule for change of variables. So if you spend a bit of time just to exploit this rule of change of variables with some distributions, you'll be able to see different kinds of functions at play, and then how you can choose these G functions that are good. So pictorially, this is what's going on with these probability flow tricks. I start with some basic distribution, a Gaussian, and I'm just going to pass it through a composition of functions, f1, f2, all the way to fk. And I'm not interested in the analytical form, I'm just only interested in the sample. So I draw samples of this distribution, I pass them through this function, and I may do capital T of them. And depending on the kind of function, I'll get this kind of complicated distribution. And as I said, the log, the entropy of this function, so that's this zk at the end, will just be log of this q of zk. And because of the rule for change of variables, it's easy to compute, because I'm just going to compute the log of the initial distribution. And this I know because I know if the initial distribution was a Gaussian. And then I just need to know the log determinant of the Jacobian. And this I know because I know f. I chose f. F has certain properties that it is invertible, and that I know how to compute it easily. So here's a picture of what that can do in two different cases. You can start with a Gaussian. You can make many different kinds of transformations, and it was chosen here to maximize the number of modes. And you can see that every transformation you do squashes and pulls apart the distribution so that you can actually represent different kinds of nonlinear multimodal distributions. And you can start with Gaussians or uniforms, and you can see this kind of splitting and shearing options. And you can extend these kind of normalizing flows, and many people, it's a whole area now as well of lots of research that I myself now even can't keep up with, that extends to other kinds of areas like spheres and toruses and non-Riemannian methods to look at invariance properties, how they apply to different kinds of physics systems and physical questions. So those are the two tricks that I wanted to look at right now. I did want to just now go back to those questions that we've been thinking about around what is the kind of work that we are doing, those kind of ethical questions. And one of those important frameworks that come up are the Sustainable Development Goals. Their official name are the Global Agenda for 2030. So we have 10 years left to achieve the Sustainable Development Goals, and there are 17 of them. And I think what's so interesting about the Sustainable Development Goals, or the SDGs as they are just more commonly referred to, is that these are the one set of problems that all countries in the world have agreed to and that are important problems. So if you are looking for important problems and you want to know what are the problems that other people have already agreed to, this becomes a very important set. You don't need to first start the work of convincing people that these are important problems. You start a little bit above the ladder on these problems. And these are some of the most important problems that I think so many of us want to work in, and that can put our skills and talent and intellect and the power of machine learning and all these powerful tools that we are learning with to good use. Of course, when we do that, it's very easy to fall into sets of traps in the way we're thinking. And one particular kind of questions that we think about in the ethics of technology, of machine learning, specifically and of AI, are called neutrality traps. So neutrality is a question where we think that the work that we do is neutral or doesn't have effects on society in some sense. And as we spoke yesterday, our work does have a set of contextual values that it's always surrounded by the mere fact that we as people are working on them. So here are some traps just to keep in mind as you're going about your own work, applying these kind of tricks and using the power of Bayesian methods to problems in machine learning. The first one is called the solutionism trap, and it says there is a failure to recognize the possibility that the best solution to a problem may not involve technology at all. It's very easy for us to say, well, oh, here's a problem, let's just apply some machine learning to it. Whereas the best first question may be to ask, do we need to solve this with technology? Are there other kinds of questions through dialogue, through governance, through addressing more basic fundamental issues? A formalism trap is one that, you know, all of us will fall into. So we just need to find ways of defending and asking each other questions, which just says that we sometimes forget that you can't represent the entire world through formalized mathematical representations. Many questions are of a fundamentally social nature, such as fairness, governance, what different kinds of justice and equality are. So we need to have a slightly more expanded view of how it is we think mathematical work and machine learning fits into play. Portability just says that we mustn't forget that if I develop a tool for Indonesia, that problem and that solution doesn't necessarily work when I apply it in Malaysia. And in fact, that portability may not work in Indonesia. It may work in your big island, and then I take it to a different island, a smaller island, and those solutions may not work for various kinds of reasons. So just remembering that things that do well in one setting can cause harm in other settings. And this ripple effect is just to understand these longer term effects, that when you insert kinds of questions, they have implications on society. Society gets used to them, and then society changes as a result of them. So these are just some of these questions to think about. I guess the very good kind of quote, which is very common, which comes up, is that technology is neither good nor bad, nor is it neutral. So let's take a 5-minute break here. I'm going to get some more water. If you have any other questions, then please leave them on the chat. We can chat about them when we come back, and speak to you in a bit. Okay, I just wanted to check, is my sound working still? If any of you can just say yes or no, that will be good.
Yes. Yes. Yes, the sound is clear.
Thank you. Okay, then let's carry on. If you have any questions which came up during this first half, we can do a bit of them. I think, Saeed, do we have around half an hour left, or is it 25 minutes? How much time do we have left? Okay, so just keep your questions coming and let's just carry on.
Yeah, we have like 25 minutes.
Okay, good. So yeah, we may not go through all the tricks that I have in mind. I'll just adapt them and we'll see how it goes, but we may be able to do them all. So this one here is a very important question. It's called in an area called stochastic optimization. There's a whole area of research in itself, and it's just going to pick up from the previous two that we did. So here now, instead, I want to compute the gradient of an expectation of a function under some distribution Q. Now, I just want us to stay at this thing. So if you are writing it, it's good to write out this integral. This gradient, I'm going to take it with respect to the parameters of the distribution Q. Now, if you were doing maximum likelihood, this gradient would be the gradient with respect to theta. That gradient is much easier to compute. You just, because Q doesn't involve theta at all, if you were computing the gradient of theta, you would just take the gradient all the way through the expectation, compute the gradient of f, and you would take the average. It would be very easy. This is what we do already in any SGD or maximum likelihood estimation. So what's different about this stochastic approximation problem is that the gradient is with respect to phi. So if we just write out the integral, it's the gradient of the integral of Q of z. And these distributions here, I'm going to call them, I don't know, measure distributions or variational parameters. They have many different kinds of names. And I'm going to call this f as a cost function, and the theta here are going to be called structural parameters. So you have these two different kinds of problems. And what's, again, intractable about this integral is that you won't know the expectation in general. You won't know it in closed form. You may not even be able to multiply these things easily and simplify it. And as I mentioned, the gradient here is with respect to phi. And so this is where there's going to be a bit of a challenge which comes up. So there's only two things going on in this integral. So what's going to come is going to sound obvious, but I think it's good to say. I'm either going to manipulate this gradient by doing some manipulations on f, and that's going to give us a class of methods which are going to call the pathwise estimation method. Or since the only other thing here is q, I'm going to do some kind of manipulations on q, and those are going to give us a different kind of methods. They're generally called measure valued methods. And one method I'm going to look at is called the score function estimator. And so this problem has so many names. It's called sensitivity analysis. It is a very core question of generative models. It's the same question in reinforcement learning. Lots of work in operations research, in finance, and Monte Carlo simulation are all about this simple integral, computing the gradient of an integral problem. So it can become a very large field of study on its own. And I have a review paper which has just come out in JMLR. So if you want to read, sort of get a very good understanding of this whole area from its basic histories over the last 50 years to the kind of things we know about machine learning and some of its future work. I think it's probably one of the papers that's my best papers. And I think we just wrote it really well. So I would encourage you to write it, and then please send us more feedback of what you think you'd do differently, write differently, and want to know differently. So let's use this kind of a trick. This one is called the reparameterization trick, commonly in machine learning. And it is this idea of expressing distributions through transformations, the same trick that we just used in the normalizing flows or these probability flow tricks. So again, the core property is that all distributions, like this distribution Q of Z, can instead be represented as by first sampling from some simpler distribution, P of epsilon, and then passing epsilon through some deterministic transformation, and it's typically an invertible transformation. So this is probably known to you. If you want to sample from any distribution, you sample from the uniform distribution, and then you pass that through its inverse CDF, and you get samples from Z. If you want to sample from a full covariance Gaussian distribution, you sample from a standard Gaussian, a diagonal Gaussian distribution, and then you pass that through a function which is a mean and a shift, mu plus sigma times epsilon. So this is a very powerful trick. So exactly, this is what I just said. In the inversion method, you sample from this uniform between 0 and 1. You then pass this through the inverse CDF, and then you're going to get a value of x, which is the distribution, and then you can sample any methods. Or for the Gaussian, as I said, I like to think of this as a set of pipes, where I sample from some base distribution z. In this case, the notation is a little bit different. Apologies for that. And then I can take it through this set of pipes, which is going to add mu, which is a mean, some diagonal variables, or some thing related to the covariance, and z. And then this will be a sample from a full covariance Gaussian distribution. And our gradient question is just going to be to trace through the pipes, to go backwards through all the things we could change to see, well, what if I added different kinds of mixtures, mu and r, into creating this liquid x here. And so this is again going to be related and exploit the property of probability flow tricks that we have, which is going to use this change of variables formula. And again, these kind of ideas have many different names, from samplers, one-liners, change of variable methods. And so to derive this estimator, we're going to use this property again, that here's the integral problem, gradient with respect to phi of epsilon of expectation of q of f of z. If I write it out, it's the gradient with respect to phi of the integral of q times f. I have one property which I know is that q of z can be equivalently represented through a deterministic function g and sampled from a simpler base distribution epsilon. So you could derive this and change this to use the change of variables formula. So instead of writing q of z, I'm going to use the change of variables, which is going to say p of epsilon d epsilon dz. That's the change of variables. Wherever I see z now, I replace it by the function g. So now I get f of g of epsilon and phi. And here again is a dz. So again, you need to change the differential. So you know that dz needs to be equal to dg d epsilon, which is this kind of change of variables you do in calculus, and you get this. So g prime here is the derivative of g. So it's just dg d epsilon in this case. So now you can just do a set of computations where you can check that, and you'll be able to simplify that using the inverse function theorem. This g epsilon and this other variable d epsilon dz is actually going to cancel out. And what you're going to be left is p epsilon times f of g of epsilon d epsilon. You could also get to this directly just by applying the rule or knowledge of the unconscious statistician, which I mentioned in the beginning, that says that, oh, if you want to compute this epsilon, you don't need to know q of z, just compute the average under p epsilon and replace z by the function. So then this now gives us a slightly easier thing to do, because now this distribution p epsilon doesn't have anything to do with phi, so I can just move the gradient through the expectation. I compute the gradient of f and g with respect to phi, and then compute averages under f. So this is now much easier because this gradient is just backprop. I can just compute the chain rule and get these derivatives, and I can easily compute the epsilon. And when I compute this using the Monte Carlo method, I can just do this even for one single sample of epsilon. So I just draw one sample epsilon, I pass it into this function, and then go backwards to compute the gradient with respect to phi, and that's it. So again, this has many, many different names that have been used. We call this stochastic backpropagation in one of our earlier papers. This method is called perturbation analysis in this field of stochastic optimization. For many of us in variational inference, we may use this as the reparameterization trick. And you can use this method when f is differentiable. Of course, because I have to compute this gradient here, and I need to do this substitution, f needs to be differentiable. I need to know q in a way that I can retransform it into this function g and epsilon. So if I don't have these kind of transformations, then I usually can't apply this method. But this method is really the easiest one to apply and is very general purpose. So if you have any kind of continuous functions and continuous distributions Q, so you can do these, then this becomes a very powerful way of doing these methods. I'm going to stay on this problem and compute that gradient in a slightly different way. Here the trick is now to exploit the property of the gradient of a log. So the gradient of a log, as we all know from basic calculus, is just the gradient of Q divided by Q. This has several useful properties, and I'd like it when you have some time and you're studying by yourself to prove these properties to yourself. It's very easy to do. Can you prove that the expectation of the score, so now the gradient of a log of a distribution is typically called the score function, and so can you compute the expectation of the score and show that it's 0? And how you will do this is by using this trick. You'll say, well, the expectation of Q of gradient of log Q is to the integral of Q, and now I represent the gradient of log Q times grad Q divided by Q. Q and Q are going to cancel. So what I get is just the integral of the gradient of Q. I'm going to exchange the gradient and the integral. Since Q is a distribution and needs to normalize to 1, the integral of the distribution is 1, and the gradient of a constant is 0. And so this is how you would prove this trick. And then you can also prove that the second derivative, this is just by writing it out, you'll get this, gives you the Fisher information. The variance of this quantity is the Fisher information. We saw the Fisher information yesterday when I mentioned something related to the invariant map estimation methods. And again, this is a very fundamental property. And because all of maximum likelihood machine learning is related to this question of the score function and this particular trick is almost the basis of almost every estimation method in machine learning. So it's important just to study these methods, to understand their properties, to really get to know them in a very intimate way. So let's use this idea of the score function in this way. So it's the same integral. Compute the gradient with respect to the parameters phi of expectation of f under distribution Q, where I want those parameters of phi. Now, the Leibniz integral rule says that I can actually exchange gradients and integrals together under certain conditions. There's the condition of absolute continuity, which is the one that we need to look at here if you're interested in the detail. But let's say I can exchange these integrals of grad and Q. So here's the gradient of Q times f of z, and I'm going to use the identity trick here again. So multiply by 1. So the integral is exactly the same. So because I know grad Q divided by Q is the score function, I can replace it by grad log Q, and this now is the form of the integral that I want. It's the expectation under a distribution that I know and can sample of times some function that I can evaluate. And I just want to re-emphasize, why did I have to introduce the identity trick and the log trick? After you take the integral, you exchange the integral and the derivative, you have integral of gradient of Q times f of f. That is no longer an integral in the form that I can do Monte Carlo estimation. I don't have a function that I can sample from and a function I can evaluate. And so what I'm trying to do here is exactly to change this into an integral of something I can sample from times something I can evaluate. This is why we have to do this kind of trick. So this trick is now very important as a trick. It has many, many different names. It's sometimes called the likelihood ratio method. In reinforcement learning, this method is called the reinforced method. In variational inference, this was introduced as the black box automation method. And the reason it's black box is very important. Unlike in the previous estimation where I had to compute derivatives of f, here f, I don't need to know f. F can easily be a simulator of a function. All I need is to be able to evaluate f at certain points, like I give it a z and I can evaluate f, and then I can actually compute a gradient in this way. The second thing is obviously I need to know q. I need to both be able to sample from it and I need to be able to compute its log derivative. And typically because I'm choosing q, I can do this easily. So Q needs to be known, it needs to be differentiable, it needs to be sampled from, but this is very powerful because F can be a simulator, it can be a physics engine, it can be a robotic system, F can be the real world, even to compute this kind of gradient. And that's the reason why it's so useful in control theory and reinforcement learning. There's 10 minutes left, so let me just look to see very briefly. I'm going to go through the few tricks a little bit faster. One other trick which is very popular is a bounding trick. So as I said, deterministic approximations are very important in machine learning. And this particular trick says that the function of an expectation can be bounded from below by the expectation of a function. You want to be able to say, how can you exchange functions and expectations? That gives you a bound. And this is a basic property of convex functions. And you'll find this in all of the theory of convex optimization, that this kind of bounding trick and other ways of doing bounds like this appear in various methods. So this trick is particularly called Jensen's inequality. So log is a concave function. So the log of an integral of p of x of f of x. So again, this is an expectation of g under p. So it's exactly this form in the purple box. I can exchange the log and the integral. So the log gets applied to g. So it's log g of x times this expectation under p. And then it's bounded from below. So this is a lower bound on this integral. So this is now very powerful. It's going to appear all over optimization in convex optimization theory. It's going to be the basis of variational inference. There's the Rao-Blackwell theorem, which relies on this to do its proof of conditional Monte Carlo methods. So you're going to see this. And you have other tricks. You can give Inferential duality. Dual methods give you bounds. Holder's inequality, the Monch-Kantorovich inequality appears as ways of creating bounds of functions like this. So this is then a bound, a trick we can use to manipulate the evidence, one of those core quantities of Bayesian analysis. So here I have p of x of z times p of z. So this is a very basic setup of a Bayesian method, and I'm going to integrate to these latent variables z. So this is the same setup you would have in a latent variable model, in variational autoencoders, even in the other kinds of generative models. I again apply the identity trick, so multiply and divide by q. I recreate the importance weight. So now I have p of x times q of z times this weight. So this looks exactly like importance sampling that we looked at earlier when we did the identity trick. But instead of now applying Monte Carlo method, what I'm going to do is instead use Jensen's inequality to take the log of p and exchange log p and z. So I'm going to get the integral under q times the log of this quantity here. And so if I just use the property of logs to separate these quantities, it's going to be the average of the log probability under the distribution q minus the average of the log ratio under the distribution q. So this then becomes a very important lower bound. It's an expectation under log probability minus a KL, which is what this distribution here is. So this is a very important kind of lower bound. It's called the evidence lower bound. It's the basis of variational inference. And then you basically want to then compute gradients of this with respect to parameters in Q, and then you would use the two tricks we just used earlier to compute those gradients. So you can see that how many tricks are being sequenced together to solve and create a solution for different kinds of machine learning problems. The last trick is called the density ratio trick. As I said, for many indirect inference methods, to compute the ratio of p divided by q is easier than computing p of x first, then q of x, and then dividing. And the property and the trick here is to know that computing the ratio of two things can be transformed into the problem of doing classification instead. And classification is one of the things we know very well how to do in machine learning. So this kind of density ratio trick, which is what this thing is the basis of learning in generative adversarial networks. It is also the basis of other methods such as noise contrastive estimation, classifier ABC methods, and you'll often see this coming up, this kind of ratio in covariant shift methods and calibration out of sample distribution. So it's very important to know these kind of tricks. So density ratio estimation, you can easily, when you have some time later to do this derivation together, I'll go through it with you here now very quickly, just so that you can follow. So here's our problem. Compute P divided by Q in some more efficient way than the naive way of first computing P, then computing Q, and then doing the division. That sounds a bit inefficient. And keep in mind Bayes' rule as a powerful tool that we can always use to invert certain distributions whenever we need it. So because I am defining things, I'm going to define a set of labels. I'm going to generate samples from P star of X and give them labels +1. And I'm going to generate samples from Q of X and give them the label -1. And so because this is by construction, I'm going to say P star of X is going to be equal to P of X given the label Y equals 1. And because I'm defining this, these two distributions are going to be the same. I'm going to say Q of X is also going to be equal to the distribution of P of X given Y equals -1, the other label. So this is the setup of the trick here. So because of that, P of X, P star X divided by Q of X is going to be equal to these equivalence representations. P of X given Y is from class 1, and P of X divided by Y equals -1. So again, nothing has changed because this is by construction defined to be the same. Now, because of Bayes' rule, I know that I can convert P of X given Y equals 1 to the inverse distribution of P of Y equals 1 given X. So that's what I get here. For the top one, it's going to be P of Y equals the positive class given X times P of X divided by probability of Y equals +1. And for the bottom, I'm going to do the same. Using Bayes' rule, it's going to be P of Y equals -1 given X, P of X times P of Y equals -1. Again, the problem is identical. Nothing has changed. And now if you just do some substitution and simplify, P of X is the same on both sides, so that just cancels. I'm making an assumption here that I can sample the same number of samples from P of X and Q of X. And so I'm making an assumption that P of Y equals +1 is equal to P of Y equals -1, so they're both a half in this case, and so they will also cancel. And so what I get is then that to compute P of X divided by Q of X, I need to compute a classifier, P, that probability that any data point comes from the class Q. And remember at the bottom, P of Y equals -1 is also 1 minus P of Y equals 1. So basically this transforms the problem of computing ratios into the problem of class probability estimation. And there's one thing that we're good at in machine learning is to compute these kinds of classifiers. I'm going to end there just by saying that these are the kinds of tricks we looked at. We looked at the identity trick, which allows us to manipulate integrals and to just explore how we can change the mathematical problems to other kinds of problems. We looked at Hutchinson's trick, which says, does the identity trick through this kind of randomized substitution of random variables. We looked at flow tricks, which introduced the idea that the change of variables formula and the unconscious statistician is very powerful for us to manipulate distributions and to create transformations of them. The log derivative trick said that it's powerful to use the basis of maximum likelihood by using the properties of the gradient of the log. Similarly, the reparameterization trick was to say the distributions, we can exploit their sampling properties and their sampling paths by sampling from a simpler distribution and getting NZ. And the density ratio trick, which said that we can transform the problem of computing ratios into the problem of class probability estimation. So there are many other tricks that I think you'll discover, that you yourself will invent as you continue your class in machine learning. So I'm really looking forward to what you will do there. I will just end with a slide here, which asks you to think again very critically about the kind of work that you will do in machine learning. And I think that was the question that I tried to put forward to all of you as we were looking through all of the cases that we went through. In this particular case, you saw this is one of these synthetic media, deep fakes, various other kinds of things, that the face of John Oliver became the face of this other person, Stephen Colbert. And then to ask these questions of dual uses, to ask these questions of neutrality that we spoke about, questions of what is the problems we are working on, ask questions of the contextual values that we are thinking about, those questions of beneficence and justice, explicability. And then to importantly think about how it is we will design the tools that we use. So I often ask people is to think about how it is we will create a new field of machine learning, a field of machine learning that is very critical of its own practice, is more responsible, takes that responsibility very seriously, and seeks ways of criticism so that we are always doing the work that actually serves the benefit of the problems that we want rather than causing harm. So again, I have lots of papers for you to follow up for this kind of second section. It has really been amazing to be able to speak with you. I love engaging with people. Thank you all for raising your voices, speaking, writing on the chat, asking questions yesterday and today. And I know we'll speak again together on Friday when some of us will meet again, and really looking forward to speaking then. But that's the end of what I had to talk to you about for this lecture on an introduction to Bayesian learning, and hopefully you'll discover more. So we can, again, if you have some time, take a few more questions if you wanted to, or we can take a break.
I think there are a few questions on the chat.
Yes, okay, let's follow. So yeah, please write your questions on the chat. The name of the paper you'll find in the slides for that particular one I was thinking of was called Monte Carlo Gradient Estimation in Machine Learning. You'll find in my integrals, I leave the DZ out all the time, just because I'm writing them very quickly and you gotta get used to it when you're writing it. But yes, you're correct. We should always write just so we know which particular thing we are actually integrating over. I don't know if there are other questions or anyone who wanted to speak and directly ask their question.
There was an off-topic questions about how you design your slides. It's a very beautiful slides, actually.
These slides, I have a few different tools that I use. I mainly use Keynote for these slides, and actually I get this question almost every lecture. So I use Keynote to design the slides. These kind of pictures that I use in various places, I use a tool which is called Omnigraphal. So this kind of picture here, for example, or even this picture, I use a tool called Omnigraphal, which is really great. You can use many other kinds of drawing tools. I have installed Acrobat Illustrator, which I think could lift my skills, but it's very complicated to use, so I haven't figured out how to use it quite yet. Maybe one day I'll be able to take a course and learn how to do it. And then you see these kind of images that I have here. They are from a website that I use called Unsplash. Typically, we want to look for photos that we can actually use that are royalty-free, that we are allowed to use. So this is really a great website to find those kind of images that you can use without royalties. Yeah, that's the combination of things to do. And then you just sort of play around, get used to it over time, find fonts that you like to use. So kind of serif fonts like this usually work out really nicely as well because they're clean and easy to use. And then, just play around with the colors. I love playing around with colors. Windy Mokue asks a question here. Windy, do you want to just unmute yourself and read your question out loud and ask your question out loud so everyone can hear?
Windy, you can speak now. Windy, you have been unmuted. Yeah, I'm not sure. Probably she doesn't want to speak, or there's a problem with the microphone.
Okay, I'll read the question out. It says that computing the integral trick for black box functions require many samples and often computationally costly. What measures or methods can be used to compute this integral, which are computationally efficient? So I think this is a good question to ask. It's not clear, actually, that it is computationally costly. In fact, this particular integral is the most widely used one in machine learning. And typically most people use this with just one sample. So this is one of the most efficient ones we can actually use. You can use more samples to reduce the kind of variance of this estimator. But having that said, it does depend on the problem. It depends on how expensive it is to evaluate F as well. So I didn't explain this when I went to the lecture, this introduction of C. So C here in reinforcement learning is called a baseline. And maybe if you have a lecture in reinforcement learning later in the week, you will see this come up. But it's called a control variant. And this is a way of reducing the variance. So the simplest thing to do is to compute C using a running average of this function f of z. And basically, you can, by subtracting the mean of f of z, any noise, basically, you just have to look at the signal that remains. And that's one way of making things more computationally efficient. And in general, for all these kinds of estimators, we have to do a lot of work around this question of variance reduction. So that's sort of one way of doing it. Again, also, it may be that this integral is not good. I think the other thing that Wendy is touching on is that if you know things about f, and like, for example, f is differentiable, then it's not such a good idea to use this estimator because you are sort of wasteful of knowledge that you have. So here it just uses everything. And because you just have to evaluate f, that's the cause of its high variance. So if you can actually compute its derivative, then sort of doing this kind of estimator is better because it actually uses knowledge. It will actually use the derivative directly and you get lower variance estimation. So there's that. And as I said, I go into a lot more details in that other paper on Monte Carlo gradient estimation on this particular question of variance estimation as well. So yeah, I think that's it. I don't see any other questions. So
yeah, I think that's basically for this session. For the next session with Shakir, it is a kind of different session, right? It's like a made the speaker session so that participant can ask another kind of question to Shakir, like how he became a researcher in the first place, for example, and how about his work at DeepMind or other things that he considers in this field. So yeah, we will meet you again on Friday. Is that correct?
Yes, great. Thank you, everyone. Yeah, I'm looking forward to meeting you all on Friday, and we can have a very open kind of conversation. So maybe if you, in preparation for that meeting, maybe you can all bring a small, I don't know, a quote of some sort that you think is useful and interesting to you. A line you read in a paper, a proverb from your country or your region or your island, depending. And, you know, let's use that as a way of introducing each other on Friday when we speak. And again, thank you, Saeed. Thank you to all the organizers. MLSS Indonesia. I look forward to actually coming to the great country of Indonesia and visiting you all, and coming to Bandung and actually visiting you all and meeting you in person. And again, however I can help you all in future with future papers, you need ideas. I'm looking forward to reading the work that you all produce, collaborating with you, and advancing our field of machine learning in a responsible and critical way together. So again, congratulations to you all. It's really important work to strengthen machine learning in Indonesia, in Southeast Asia. So much more work needs to come. You have a lot of supporters across the world. Whenever you need it, please call on us. And again, congratulations to you all. So yeah,
thank you.
Bye. See you on Friday.
Bye. Okay, next session will start in the next 50, I think, and we will have maybe more different kind of topic, which is reinforcement learning. We will have Feral and also Matt from also DeepMind. Okay, so please join us again in the next 50 minutes.
We are channeling the company's artificial intelligence efforts into one recognizable organization, Qualcomm AI Research. Qualcomm invents breakthrough technology that transforms the way the world connects and communicates. Going beyond mobile chipsets, we're inventing AI technology that can be used across a wide range of products and industries, from mobile and automotive to smart homes and cities, ultimately changing the way people live for the better.
Machine learning has already entered every corner of the Qualcomm enterprise. I personally believe that Qualcomm is uniquely positioned to become a key player in on-device AI, which brings with it tremendous opportunities, such as increased data privacy for users, reliability of service, high speed, and efficient use of bandwidth.
Today, machine learning algorithms, such as deep learning, use huge amounts of energy to power them. And as AI increasingly moves to low-power edge devices, energy efficiency becomes all the more important.
The challenge we face in the future is about squeezing as much as computation as possible out of every joule of energy. And Qualcomm has a long history of delivering technologies that do just that.
Our mission is to push the envelope of AI and machine learning in the areas that will significantly improve everyday life. We are asking challenging questions, like how do we preserve communication privacy? Can we use deep learning to compress videos? How can we eliminate uncertainty when making life and death decisions? And how can we use this knowledge to optimize Qualcomm chips that run machine learning algorithms?
Qualcomm AI Research is an inspiring environment where researchers collaborate, innovate, and share their findings with the world through high-impact publications. But we do so much more than just writing papers. We actually build AI solutions that are used in billions of devices. In your cell phone, your smartwatch, your drone, your car, and all the other innovative technology of the future.
So if you're interested in pushing the frontiers of artificial intelligence, machine learning, or deep learning, and above all, if you feel passionate about the prospect of bringing ideas to life and impacting billions of people, then Qualcomm AI Research is the place for you.
Semua hal berangkat dari sebuah awal. Begitupun kami menjadi pionir. Memutar roda penggerak bangsa dan terus melaju. Kami hadir seperti sebuah keluarga. Dan terus fokus membangun perekonomian negeri. Menjadi yang terdepan, mewujudkan mimpi-mimpi besar. Dari atas awan kami terus bergerak dan berinovasi, melihat negeri ini tumbuh dan berkembang. Inilah kami yang tak akan pernah berhenti, mengantarkan Indonesia ke puncak kejayaan. Karena dimanapun dan kapanpun, kami selalu hadir melayani dengan setulus hati.
History, most of the time, is born out of the simplest of acts, just like the birth of our story, starting with the pursuit to close the distance through voice and make exchanging of informations at your own fingertips. And who could have known that was just the first step of our long journey? We had to jump even higher, to open new dimensions of opportunities to explore the world. And we keep on transforming through different times so that we can bring joy and progress for all walks of life. The world is always spinning, just like the sun. Your loyalty in us has always been our light to keep on innovating. No more simple beginnings, further and ahead. We have to keep on running, for you, for Indonesia, with the same vigor that has been driving us from the day one we began. Our 55 years selalu ada untuk Indonesia.